When you look at a commercial airliner waiting on the tarmac, you are looking at over 500,000 pounds of metal, wiring, luggage, and fuel. Getting an object that massive to leap into the sky seems absurd on its face. At a standstill, the baseline laws of physics are actively working against it. Gravity is constantly pulling that tremendous weight downward into the concrete, while the surrounding air acts as a thick wall of drag, resisting any forward movement. To overpower the atmosphere, engineers rely on the jet engine. Inside these casings, spinning turbine rings compress incoming air and mix it with fuel to create explosive forward thrust, brute forcing a path through the drag. But thrust alone doesn't lift the plane. The engines must accelerate that 500,000-pound machine from 0 to over 300 kilometers per hour in seconds. The sole purpose of that extreme speed is to force massive amounts of air to rush over the wings. This animated cross-section shows exactly how a wing catches that air. The leading edge splits the airflow, and the specific upward curvature of the wing forces the air traveling over the top to move faster. That sudden acceleration creates a zone of low pressure right above the metal. Meanwhile, the air moving underneath retains a higher pressure. The atmosphere naturally pushes up into that low pressure void above. That upward surge generates a physical force, lift, strong enough to conquer gravity. Taking off is a highly calculated manipulation of atmospheric pressure. We force the air to hold the weight. At 40,000 feet, the environment becomes completely hostile. The sky darkens, temperatures plunge below -50 degrees Celsius, and the aircraft cruises faster than a rifle bullet. Building a machine to survive these extreme pressure and temperature differentials requires a facility vast enough to house entire fleets under a single roof. Every joint and rivet must maintain a pressurized seal against a near vacuum. But a rigid structure is a fragile structure. If the plane's frame were made of perfectly stiff metal, hitting a sudden pocket of turbulent air would cause the wings to snap under the violent kinetic stress. To solve this, engineers incorporate materials like carbon fiber. The wings are intentionally designed to be highly pliable. When the plane hits rough air, the wings bend and flex, absorbing and dispersing the kinetic energy before it reaches the cabin. The airplane is a meticulously crafted, pressurized survival capsule that renders a deadly layer of the Earth's atmosphere entirely safe for human travel. Achieving that safety requires a philosophy of systemic redundancy. Aviation engineering assumes that external threats and mechanical failures are inevitable. Commercial jets are struck by lightning regularly. To protect the passengers and the highly flammable jet fuel in the wings, the outer shell of the aircraft contains a conductive metal mesh. It instantly catches the strike and dissipates millions of volts out through the tail, leaving the interior untouched. Even in the ultimate mechanical nightmare, a dual engine failure, the plane doesn't drop out of the sky. Those massive wings allow the heavy aircraft to become an efficient glider, trading altitude for forward momentum to reach a runway. And if a system does fail, we have the flight data recorder. Encased in reinforced steel and built to survive impacts, crushing pressure, and intense fire, it perfectly preserves sensor data from the flight. Modern aviation has achieved an unparalleled safety record by ruthlessly engineering machines that anticipate, absorb, and learn from every conceivable point of failure. We have mastered the physics of heavy lift and structural survival. Today, the engineering adversaries are emissions and efficiency. The aerospace industry is aggressively transitioning toward electric and hydrogen-powered aircraft, aiming to eliminate combustion engines from commercial flight entirely. The core hurdle is weight. Current battery technology is significantly heavier than liquid jet fuel. To carry that extra mass, engineers have to rewrite the aerodynamic formulas for wing design and lift. Decision-making in the cockpit is also shifting toward distributed intelligence. Artificial intelligence is moving beyond the roles of standard autopilot to manage the logistical complexities of global flight paths. This network map illustrates how AI systems can simultaneously analyze massive datasets. By processing real-time variables on weather patterns, fuel consumption, and global air traffic, these systems proactively reroute thousands of flights around shifting storm zones before a human pilot even detects the turbulence. In December 1903, the Wright brothers flyer covered just 120 feet in its first journey. Today, an intercontinental jet covers that same distance in less than a single second. The Concorde represents the peak of that mechanical ambition. Designed to cruise at twice the speed of sound, it turned transatlantic crossings into 3-hour afternoon commutes. The next time you look out of a passenger window, remember that this machine is the physical result of solving a series of once impossible engineering problems. We didn't conquer the skies by avoiding danger, but by learning how to outsmart the air itself.